Okay, so till now we have been discussing about amplifiers, current meters, control sources of various formats, but they are essentially small pieces, right? They are essentially small pieces of circuits, which, even though they are pretty useful, they are not the final thing that you will be seeing in any products. Like if you check the amplifiers in your cell phone or the op amps that you might have used in ESC 201 labs, they are neither of these small circuits, but those are made with the contraptions that we have learned till now, right? So if the concepts of common source amplifier, the concept of common gate like CCVS, VCVS, so on and so forth, they are all used to make those building blocks. So hence the focus till now on the course has been to ensure that we understand how the building blocks are made, the principles that govern them, so that we can use them to make bigger circuits, right? We can use them to make better systems. Now, one of the problems of a good amplifier, the one that we have studied in this course till now, I mean, the only amplifier kind of that we have studied in this course is a common source amplifier. So in a common source amplifier, our gain is minus GM times RL. Now, GM times, let me just say R. So the expression of GM has, I mean, you can write it in any format, but let's say I write it in this format. Now, as I have mentioned multiple times, mu is temperature dependent, right? And we also know that from your past experiences, I'm sure you know that resistance is also temperature dependent, right? It has a positive temperature coefficient. That is, if you increase temperature, the value of resistance increases. So temperature is only one of the ambient dependencies. These things can change if the humidity changes, if the pressure changes. There can be some effect, right? So the moot point that I am getting to here is that the gain is not constant with changes in ambient, right? So gain is not fixed if changes in ambient conditions. Now, one might say, what's the problem? If the gain is not fixed, as long as I get a range of gain, the problem is you can think of it in the live example that I am demonstrating right now. That this is an amplifier, right? I am talking into a PA system. Then my voice is getting electronically transmitted to the loudspeakers. It's getting amplified, and the loudspeakers are bursting out some sounds. Right. So this is an amplifier. I'm definitely not speaking in the same decibel levels that is coming out, right? So there's some amplification that has been happening. Now, what would have happened if this amplification factor would have changed with time? So sometimes you would have seen a very loud voice coming out, sometimes you would have seen a feeble voice coming out, and so on, right? So this is not something that is desirable. So we would like to ensure that your gain is stable. Whatever the value of the gain might be, it should be stable. If you have to design a product and sell it in the market, you cannot say that, hey, today it will have so much of gain, tomorrow it will have so much of gain. Your iPods or whatever, your music players should have a stable gain, regardless of how much you turn the knob or how much you slide your volume button. Similarly, it goes for any electronic systems, not even electronic system, any systems which require amplifiers across domains. So this is something not desirable. But the good thing about this is it at least gives you amplification. You can get decent amount of gain from a CSM. So positive is, so this is negative, right? This is a negative aspect. What is a positive aspect? Positive aspect is we can get decent gain, right? So that means AB is greater than 1, right? So this is good, but the negative aspect is it changes, gain is not stable. However, forget about this amplifier business. Given that you know the components that we use in circuits, right? Resistances, capacitances, MOSFETs, and you know the MOSFETs also have certain type of characteristics. You should be aware of the fact that none of these characteristics, right? Neither GM nor R, not even capacitance or inductance, are stable with temperature. All of them vary with temperature, right? So the question naturally that arises, if everything varies with temperature, how can we even think of making an amplifier which has a gain is stable, right? How can we think of making anything that doesn't change with temperature, right? That's a logical question to ask. The problem I am facing is my gain is not constant, and forget about gain. If the problem I am facing is some parameter, some property of a circuit is not constant with temperature. But then the stuff I am making the circuits with, none of those things are constant with temperature. Then how can I even think of making an amplifier whose gain is independent of temperature? Does that problem make sense? Okay. So do you have any ideas in terms of not about making an amplifier, about anything, given that it has to be electronically made, right? That can be constant with temperature. Yes. Exactly, right? A ratio of parameters which vary identically will be constant with temperature, right? If we take a ratio, if a voltage divider, right? You take R, you take the midpoint, you get R by R plus R. Both the R's vary in the same direction regardless of the change of ambient, right? In the same proportion rather, right? If it varies by the same proportion, then the ratios will be independent of temperature. Similarly, if you take ratios of GMs, right? They will be independent of temperature because the temperature variation of those two GMs will be mostly identical. Okay, so the good thing about taking ratios is however, ratios of parameters or ratio, assuming all changes linearly, yes, obviously. Otherwise, okay, let's think about it, right? Even if it doesn't change linearly, okay. So let's see, right? So let's think it through once. So if R1 by R1 plus R2, let's say R1 is R01 plus some alpha delta T plus beta delta T squared. And R1 is again, so R01. R2. Provided these alphas and betas are identical for both resistors, then it really doesn't matter whether the changes are linear or non-linear. Right? Provided these coefficients of changes, right, alpha and beta are identical, then it really doesn't matter. No, all the delta, if they are placed, their delta T is your changes temperature, right? So if two resistors are sitting next to each other, their temperature will be same, isn't it? The ambients are same for both of them, right? So yes, right. So essentially, this becomes equal to R01 by R01 plus R02, right? So they become independent of ambient condition, provided both of them see the same variation, right? If they are not seeing the same variation, then you have a problem. Right? Sometimes this is a design problem. People face this problem because when you have made a resistor, you have laid out a resistor in such a way that it's one corner of the chip, and another resistor is another corner of the chip, and maybe there is more power consumption on that side of the chip and less here. So you'll have thermal gradient across the chip. So the temperature coefficients might, this delta T will not be same, and that you can have different ratios because of that. But that is actually a design problem which IC designers have to take care when we design ICs. Okay, so you have to make sure that whatever you are designing to for tracking closely, you have to ensure that they are placed very close to each other, so that when whatever bad things happen to the neighbor, the same thing happens to me. Okay, or maybe the other way around. Okay, so the good thing about ratios is, the positive thing about ratios is, ratios are independent of variations in ambient. However, the bad thing about ratios is, from the perspective of making an amplifier, ratios are always less than 1. Right? If you get a voltage divider, R1 by R2, R1 by R1 plus R2, you will always get less than 1. You'll never get more than 1. Okay. So to summarize, amplifiers need gain of more than 1, but common source amplifier or any amplifier that we have seen are not in the form of ratios. Since the expressions are not in the form of ratios, they will be dependent on ambient variation. Now, ratios are independent of ambient variations, but if you make R1 by R2, or R1 by R1, R1 by R1 plus R2 in terms of voltage divider, or something made out of GM, or doesn't matter, so you will always get less than 1. So the question that we are asking is it possible to marry the good things of these two? Right? Can I make an amplifier which is dependent on the ratios, whose expression is equivalent to the ratio of components? If we can make an amplifier whose expression is dependent on the ratio of components, then we are good. We will get amplification of more than 1, and it will also be quite stable. Okay. Okay. Yes. That we will see. That's what we'll see, right? That's the problem statement. Yes. Okay, tell me. But how do you make that? I'm not saying ratios are less than 1. It's not a general statement. It is how do you make a ratio in an IC or in a circuit from whatever we know till now? Yeah, it's like voltage divider, right? Or a current divider, something like that. The moment you are dividing, then you have a problem, right? So otherwise, obviously, you can say I can plug in any value there, and it will become more than 1, right? So that's what I mean. The question is, how can I make a circuit so that I can plug any value? Okay. Okay. So now, so let's say I want, let's say with this context in mind, we want to design a voltage controlled voltage source or an amplifier. Let's not get into the voltage controlled voltage source business. We want to design an amplifier where V0 is equal to A times Vi, where K is greater than 1. Right? We want. Right? This is the goal. Okay. So now, before proceeding, let me take you back a few classes, I think maybe 10 classes, where we talked about the principles of using negative feedback. So, for example, I'll again lead with an analogy, which is not electrical, but hopefully it will make sense. For example, you are riding your cycle, right? So let's say you are riding your cycle, and this is the path that you are taking. Maybe the turn around the hall one bend, right? So you are riding this cycle. So generally, what is it that you think of while riding a cycle? You have to take a turn. Obviously, you don't, while you are riding, you are not sitting and calculating the exact curvature right? And giving the exact amount of torque to the handle in order to make a turn, right? Nobody does that. But then if we don't do that, how are we actually making a turn appropriately without hitting anybody, right? Because laws of physics hold, you'll have to still apply the appropriate amount of torque to the handle of your bicycle in order to turn. But nobody ever sits and calculates, right? But we are pretty accurate. So how do you do that? Both of you are correct. He is saying that we approximate the small turns, and he is saying we minimize error. So let me lead with that approximate the small turn first. So what are we essentially doing? We are seeing what is the next step, what is the incrementally, what is the next direction I have to go, right? And then I am taking an action. I am taking an action, but I am taking the action not by calculating. I am taking the action by applying an arbitrary force to the handle. And I am seeing whether that force is appropriate or not. And how am I making the call that the force is appropriate or not? I'm making the call by seeing after I applied the force, how much the handle has turned. Right? You must have seen when you ride a new bicycle for the first time, you don't know exactly how smooth the handle is or how difficult it is to turn. So initially, you will always waver a bit, right? Because you don't know, your body doesn't know how much exactly you need to turn. Okay. So the problem is, or rather not the problem, with the intuition with which you ride a bike, is you see where you need to go, what is your desired path, and you apply a torque and see where is your actual path, right? When you turn, the bike goes in a certain direction, and that is your actual path. And if the desired and actual are different, you take a corrective action, right? You either apply more torque or you apply less torque, depending upon what is the characteristics of the handle, right? So essentially, you ride your bike with the concept of minimizing error through negative feedback. Okay, why I'm saying negative feedback? Because you are seeing where you are going, you are taking an action based on the difference between where you are going and where you want to go, and you are taking a corrective action in order to minimize that error. You are negating that error. That's why we are using negative feedback. You are seeing the output, feeding back that information to the input with the hope of negating the error. Okay, so we do everything using negative feedback. Okay, and that essentially makes it a stable system, right? If tomorrow you have to take another turn through another curvature, you will use the same principle. You will not again sit and calculate the curvature. Okay, if it rains and someday your ambient is slippery, again you will use the same principle, right? You will not ride very fast probably, but you will use the same principle that probably I don't need to apply as much amount of torque to my handle as I had to do the previous day because my ambient is slippery. So this is important, that you have to, regardless of whether you are doing this course or you're doing something else in design, you always use principles of negative feedback in order to make a very good, stable design. Okay, so now how does it translate to our scenario? So firstly, in negative feedback, you need two things. One is you need to know where you are going, and you need to know where you want to go, right? You need desired, you need actual. So what is our desired in our case? My desired V0, or my desired output is K times Vi, right? And what is my actual output? Actual output is some V0. Okay, these two are not matched all the time, right? We have to ensure that by design, they are matched. So which means that, what is the second principle? We'll have to figure out how to define an error. When you're riding a bike, your body is automatically doing it. Your mind is automatically doing it through the sensor interfaces of your eyes and your hands. But in this case, we are in charge of designing both of those things. So what is the error? How will you define an error? In this case, Our error is, tell me how shall I define an error? Right, so desired minus actual, let's say, you can go either direction, but it's a desired minus actual. And we want, let me call this VE, and we want to drive this to 0. Right? We have to take some action on top of the error in order to drive this to 0. Okay, right? The corrective action is the one that will drive it to 0. Okay, so now, so how do I mean, in the block diagrammatic form, how do I get this? I can say that this is let's say K times VI, this is V naught, this is VE. And we'll have to do something on VE to get it to 0. Okay, but do you see a problem right at the outset? This is supposed to be the desired, right? This is supposed to be the desired. And this is supposed to be the actual. Do you see a problem of setting up the problem statement like this? Yeah, right. So you need to know the actual. Let's say initially V naught will not be equal to KVI, right? That's fine. But the problem is, how do I get KVI? I don't have KVI. If I had KVI, then this wouldn't have been a problem. Right? So I am trying to compare with the desired, and the desired I am planning to manufacture. I don't have the desired one right at the beginning. Right? So this is the problem. So the way we get rid of this problem is redefining the error and say that let's define the error as that's a new error, let's say. We'll define it as Vi minus V naught over K. And then drive this to 0. Right? If I drive this to 0, I'll still get V naught equal to K times Vi. Now the natural question that you should ask is, why am I doing this? Right? What is so holy about K times Vi or V naught over K? Here, the concept of ratio kicks in. Because let's say K is equal to 2. We want V naught equal to K times Vi. We want V naught equal to 2 Vi. So I know that 2 Vi I cannot really, I don't have. But do I have V naught over 2? Can I have V naught over 2? I can have V naught over 2, right? Because I can have a resistor divider. I can have a resistor divider attached to V naught. Center point of it will be V naught over 2. And that will be stable. Yeah. So the problem is, how do I manufacture KVI? With all the things that we know, how do I manufacture KVI? I have Vi, I'll have to pass it through a gain block of gain K. Right? But I don't have this gain block of gain K. Right? We want to manufacture this. But if I, let's say, have V naught, and I want V naught over K, all I can do is, let's say this is K minus 1 times R, this is R. Right? And I will have V naught over K. And this V naught over K will be independent of ambient variations. Right? You had a question? Yes. So they are, as far as the driving, the consequences of if you drive both of them to 0 are identical, you will get V naught over Vi by K. But the issue is, in order to get this, if you want to realize this type of error voltage, you need KVI to start off. Right? We don't have that. One might say I can use a common source amplifier, but the problem is the K of the common source amplifier will vary. That we don't want. Right? So how are we going up, getting rid of the problem? We're getting rid of the problem by saying I'll redefine my error as Vi minus V naught over K, because Vi is an input I know, and I can always shift the voltage of V naught down reliably. Okay, fine. So now if this is fine, Then let's say we have V naught. This is V naught over K, and I'm redefining my error. So this is Vi, this is V naught over K. Okay. So now we have the initial pieces of negative feedback loop. We have found out the error voltage, right? We have set up our system in some way that we have to do something to the error voltage in order to get the right V naught, which means now we'll have to figure out what is the, in terms of riding the bike example, you have to figure out what is the characteristics of your handle or how strong you are, right? So you have to put something here. You have to put something here and figure out what you have to put here. What is the characteristics of this stuff inside the box? So now let me take you again back to the example of riding the bicycle. And we are not particularly bothered about the frequency component of it. That is, we are not bothered about the rate of change right now. So we are all bothered about steady state characteristics of this block. So now going back to that example of riding your bicycle. So let's assume you are in charge of riding the bicycle, and you are not feeling particularly well, that you don't have enough force, or maybe the bicycle handle is too stiff. You are not able to turn the bicycle. Will you be able to ride properly? No, right? If you have infinite strength, will you be able to ride properly? Why not? No, if you have infinite strength, yeah, but you are in charge of how much force you can apply. Then you can, right? So you want infinite strength, right? And what does it mean when I say in terms of amplifier, you have infinite strength? You need infinite gain, right? So here you need infinite, if you have infinite gain, then seems like if I hook this up, it might work. Okay. But this is as far as synthesis of a network is concerned, right? This is all storytelling. You'll have to, next part that kicks in is we'll do the analysis and see whether it makes sense or not. Yes. Okay, so again, going back to that analogy of riding your bicycle, what is the error? The error is essentially the direction that you want to go, the angle at which you want to turn, and the angle at which you are actually going. That delta theta is your error. You want to minimize that delta theta, right? So what will you do? You will apply a force or apply a torque, right? And if you don't have enough force inside you, right, you're feeling particularly weak or something, then obviously you'll not be able to turn. Right? But if you have infinite capacity, regardless of how stiff the handle is or whatever, then you will always be able to turn. Right? Seems like the solution is infinite strength. Right? In terms of amplifier, it translates to infinite gain. Okay. So let's see. Let's do the analysis and see. Let's say this voltage gain is AV, and AV tends to infinity. Okay. So what is my equation now? So VE times AV is equal to V naught, and VE is VI minus V naught over K. Kind of, yes. So if the error, so it's actually the other way around, right? So give me 2 minutes, it will make sense. Okay. So this means what? This means VI equal to V naught 1 plus AV over K. Did I? Okay, yeah. Some mistake here. So let's stick to this format for the time being. Okay. So what happens if AV tends to infinity? Then Vi minus V naught by K tends to 0, which means V naught tends to K times Vi. Right? So coming back to his question was, why are we looking for infinite gain? We are looking for infinite gain because of this specific reason. Right? So in an open loop sense, if I increase Vi, if I kick my system in the right direction, in the sense that I observe VE, I observe the error, and I have amplified the error with a very large gain, then obviously I should get a very large output, right? If I delta theta is small and I kick it in the right direction, I get a very large, I mean, one might say I'll rotate my handle almost multiple times over 360, right? But the problem is we are not stopping there. Not the problem, but the good thing is that we are not stopping there. We are always monitoring. So which means that the output is always getting fed back to the input. And in a stable system, output cannot go to infinity. So output is stable. Output is within finite range. And if you have something with a finite range and you are driving that thing with an infinite force, which means the input to that block has to be 0. Right? Otherwise, you will get an infinite output. In order to get a finite output, in order to get a finite voltage at the output of an infinite gain block, the input of that infinite gain block has to go to 0. This is the concept of op amps with virtual grounds, right? So if you have infinite gain at the and given that your circuit is stable, the input to that infinite gain block has to go to 0. That's the only possible solution. Okay, that is the analysis part kicking in. But as far as if you have to set up a system in order to ensure that the system works properly using negative feedback, this is the thought process that should play around in your mind. Okay. So now if I formalize this, so this looks to be an amplifier. If AV tends to infinity, then this VE is tending to 0. Right? So there is one important aspect. Once you have set up the negative feedback loop, or maybe somebody has given you a negative feedback loop, you have to ensure, the first thing that you have to ensure is the direction of the loop fine? Which means, are you correcting the error in the right direction, or you just going in the opposite direction, right? I could have as well said that instead of AV, I'll have minus AV, right? So in that case, it obviously wouldn't have been fine. So I need to turn my handle in the right direction. I'm seeing the error, it's fine, but if I turn it in the other direction, there's no point. So the direction of the loop is important. So how do you figure out the direction of the loop? Yes. Okay, right. That's the problem of if you set it up using maths, right? So in order to figure out whether the direction is right or not, you'll have to go into stability analysis. We'll go there later on, like in maybe 1 or 2 classes we'll go. But how do you figure out without doing the maths, right? Whether it is it's going in the right direction in the first place, right? So which means that you're looking into the network, you'll have a circuit or the system, you'll have to figure out that if there is an error, right? Let's say I am not going in the right direction. If there is an error, is the sense of the correction in the right direction? Which means, is the error getting magnified or is the error getting reduced? As long as I know the sense is right, I know the direction of the feedback is right. Rest of it is component values, right? How much, whether it's large enough or small enough and so on. So the first thing is, what is the direction of the negative feedback loop, and is that correct or not? So the good thing about a loop is that everything is connected. You don't know you don't know I mean, where the signals flow starts, right? It always goes round and round. So you can imagine that you have injected an error at any point. Let's say I inject an error at this point. Let's say this voltage increases. If this voltage increases, this voltage increases, this voltage increases. So it's in the night. I mean, it's going through a summer with a negative direction here, right? Since this decreases, so this will decrease. So it looks like I'm negating the error. I'm reducing the error, right? So had this been negative and positive, right? Had the directions of the summer been this, then I would have increased the error. So that wouldn't have been a right direction of hooking up the loop. Okay. So given that you have any loop, this is the first thing that you should check. Right? You have already done loop analysis, in the sense that not loop analysis. Many of the circuits that we have solved till now are in negative feedback, right? Because VCVS, CCVS, they are all in negative feedback. So you can go back and check whether using these principles, whether they are hooked up in the right direction or not. Okay, fine. So this is good. And by the way, I'm sure that by now you must have recognized that this is the form of this classical negative feedback system that you have learned in 250, right? So what is, typically the negative feedback systems that we learn are of this, the block diagram is like this. So V naught over Vi in this case is G by 1 plus GH. And if GH tends to infinity, V naught over Vi tends to 1 over H. Right? So can you relate these two? What is G and what is H? Yes. Pardon? Okay. So if GH tends to infinity, it's also the same, right? Yeah, it's 1 over H. Now H is infinity, then it goes to 0. H is 2, 3, then it goes to whatever. H is half, it goes to 2. Yeah, fine. So depends upon how you have set up the H. So we are saying that if G is tending towards infinity, then V naught by V. Yeah. So that's how it looks like. But what is the problem if I say GH tends to infinity? Does this expression hold if GH tends to infinity? Yeah, that's why I have tending, right? That's because you'll have to give one answer, but it never goes to exact value. It always tends. That's what the limit is, right? You can, right? In certain cases, obviously, yes. Yes. I mean, G goes to infinity is a subset of this. Yeah, but don't take H equal to infinity. You are in control of the system, right? Why would you put H equal to infinity then? Right? So this is a generic thing, right? G equal to infinity, only G equal to infinity is a subset of this. Okay, so the parity between these two, the loop on the top and the bottom is, what is G? G is AV. And what is H? What is H? 1 by K. Right? So this guy over here gives you 1 over K, gives you the H, and this guy obviously gives you the gain. Okay. So now good thing is that this looks like we have been successfully able to marry the good things of a gain block and the good things of a ratio block. Okay, we are getting H through a ratio, and we are using the gain block to drive an error which we have manufactured somehow. Now, why is this good? The good thing is because do you need an exact precise value of AV? Or you just need AV to be really large? You just need AV to be really large. It doesn't matter whether AV is 1 million or 2 million or 10 million, right? As long as it is higher than some threshold value, you are good. Right? So that is okay, right? That is okay because we can design amplifiers which is higher than certain value. It probably not, it did not be an exact value. As long as it is higher than something, we are good. That our common source amplifier can do reasonably. Okay. So you are allowed some disturbances on AV as long as it's higher than something. But you are not allowed any disturbances in H. Right? That's why you have to make the H as a ratio. Okay. Okay, good. Now, let's say I have, now the time has come to basically replace the AV with a common source amplifier. Yes. However, here is less than 1. Why? Yeah, K, no, K is not less than 1, right? Yes. So assume K equal to 2, for example, right? If K equal to 2, this becomes R and R. Right? Okay, so let me spend 1 more minute on this. Let's assume, okay, if K equal to 2, your V0 is equal to 2 Vi, right? VR tends to 2 Vi rather in this case, right? It's always tends to, but we'll replace it with exact later on. Okay, so now, so naturally, I mean, whatever from whatever discussion we indulged until now, the most important thing that came out, other than the fact that how you have to set up the network, you need a lot of accuracy in the feedback path. What is the feedback path? Whatever you are getting from the output and feeding it back. In this case, you need a lot of accuracy on H. You cannot afford any variation in H, but you can afford a variation in G as long as G is really large. Okay. Okay. So now let's replace this AV with the only block that we know, that is the common source amplifier. Right. So okay, the first thing that I need to check here is the sense of the loop, right? Do you think the sense of the loop, right? If I let's say this is plus, this is minus. So in order to figure out the sense of the loop, input is immaterial. You can disregard the input. You can assume the input is 0, right? Or desensitize, because the sense of the loop is independent of what input you have applied. So it should be, the only purpose of the loop is to reduce any disturbance in the loop. Yes. Right. Okay, let's do it step by step, right? You can imagine you have increased this voltage, right? Which means what will happen to V0? V0 will reduce, right? So this reduces. This reduces. So what happens to the error voltage? It increases, right? You have negative here. So negative, it increases, changes direction, which means this is clearly not in the right direction. This will not be able to, this loop will not settle in the right direction. It will only keep on amplifying the error in the wrong direction. Okay. So if this decreases, you have negative here, negation, right? there will be a sign change. Yes, this will go up. Yeah, so the other way to fix this problem is simply to do this. I'll just change the correct. Yes. So you want the error to incrementally go closer and closer. I mean, Vi and V naught to go closer and closer, and error to shut down to 0. Right. So it's difficult to imagine right now because there is no time dependence built into the loop. Right. Everything is instantaneous. So we'll build in time dependence later on. But for now, keep that in mind that as long as under the DC condition, right? This is all DC condition. There is no time dependence. So you inject an error anywhere in the loop, go around the loop, and come back to the same place where you have injected the error and see whether the error is going up or down. That's all. That's the sense. Strength of the loop is up to the analysis, right? You have to once the sense of the loop is fine, you have to find the strength of the loop, right? Whether the loop gain is infinity or very high, right? Okay. By the way, I didn't introduce the terminologies. So this GH is called loop gain. Which is also very commonly referred to as L. Okay, so as long as we are okay with this, okay, you mean right now or the one previous to this? Okay, so one previous to this, let's say do this. So let's increase this voltage. Are you comfortable with the idea that this decreases? Not. So this is the common source amplifier, right? So what is if input of the common source amplifier increases, what's going to happen to the output? In the direction it will go. Right? Forget about this entire thing. Just consider it here. If this voltage increases, what happens to the drain? If the gate voltage increases, gain will remain same, but if the gate increases our common source amplifier, the drain will go up or down. It will go down, right? It's minus GM times RL, right? So if the gate of a common source amplifier increases, the drain goes on the opposite direction, right? Then decreases. So that's why we had to change the direction of the loop. So here, in this case, there is the implicit assumption that G is positive, right? So if this increases, this increases. That's the assumption. But in this case, in our common source amplifier, it's minus G. Okay, fine. So this is negative. And by the way, you need not inject, in order to check this, you need not always inject the error at this node. You can inject it anywhere in the loop. You can start off here. Let's say this increases, this increases, this increases. So it comes back and this decreases. Right? Anywhere in the loop. That's the good thing about negative feedback loop. You can do this analysis by injecting error. I mean, hypothetical analysis by injecting error anywhere in the loop. It's a property of the loop, so it doesn't change where you disturb it. You don't even need an input in order to figure out how the loop behaves. Okay. So now I had, I mean, without too much of thought, I had simply connected, I have loaded the common source amplifier output with a resistor stack of value, what, K-1 R in series with R. So effectively, I have loaded with KR, right? So if I just sketch this. This is what I have done. VE here. So given that whatever you know till now about CS amplifier, is this a reasonable way of setting up my circuit? Yeah, so what will eventually happen is that there will be some current diversion here. You would want certain current, right? Through the MOSFET in order to give you certain GM. If you just simply load KR, you'll have a problem. You'll have a biasing problem. Now one might say that, hey, why do we need this? I can do this, right? All the current that flows through the MOSFET should come from RLs to the same stack. It sets up the bias nicely, and this is fine, right? This will work, right? But the issue is, if KR is, so in order to get really large gain, right? In order to get really large gain, you need to ensure that GM times RL is large, right? And for a given GM, you need RL to be large. And let's say VDD you have control over, you can change VDD. Now, if you put this KR, in the incremental sense, your load becomes KR parallel RL, right? So you are essentially reducing your gain, correct? Because the feedback, this H is loading the G, right? The feedback network is loading the forward path. When you express in the block diagrammatic formation, it implicitly assumes that H doesn't load G. You have, even if you put in an arbitrary value of H, the gain of G remains G. That's the implicit assumption in a block diagrammatic sense. Which means that even though it's not specifically mentioned in most places, whenever you put this block diagram, you are saying that all G and H are voltage controlled voltage sources, right? So it doesn't matter what you put, the voltages, whatever it was supposed to be in the presence, in the absence of any of those blocks, remain the same, right? H can be 1, 2, 100, 0, doesn't matter. V0 is always V times G. That's what a block diagram means, which means in circuit parlance, you are assuming they are voltage controlled voltage sources. But in this case, you see that it's not a voltage controlled voltage source. Depending upon how you change H, the forward transfer function will change because they are not unrelated. Okay, so that is why when you are doing any real circuit analysis, you cannot do in most cases, you will not be able to isolate G, because the value of G, the gain of G will depend on H also because of this loading factor. Okay, so that's why we mostly talk about GH and not only G. G times H. Okay, or L. Okay, let's stop here. Tomorrow we have a class, right? We'll meet tomorrow. Yeah, we don't want KR to load incrementally as well as quiescent. You are right. Yes. So that we can actually easily do, because as long as we make sure KR is much larger than RL, we are good. Right? So that is something that a designer has to take care. Okay. Okay, fine.